So, we have gone through certain exercises, numerical problems, and we will go to the next topic now. Device and system performance. All the while we were considering the solar flat plate collectors or concentrating collectors, we were focusing or concentrating on the collector performance. So, no doubt it gives you the useful energy, but then the complete system comprises of not only the solar collector, but several other components. No doubt solar collector, you may call it the heart of the system, and it consists of several other components. For example, storage tank, a pump or a blower. You may have a heat exchanger, more than one in fact. There may be auxiliary, either in series or parallel, and you can most importantly control, which ensures T supplied is what you wanted in the design of the system. And all these things, components, can affect the performance of the system. As a very extreme example to drive home the point, somebody designed and calculated it requires, let us say, 50 square meters of collector area for bathing in a hostel, and then no storage tank. So, unless the demand matches exactly with the solar radiation variation over the day, you will not have any water that is available to you, let us say if you take a bath early in the morning. But you provide a storage tank approximately of, let us say, 1 day capacity. In other words, if 50 square meters are going to give you something like 50 into 60 liters of water at about 60 degrees C, you have a tank capacity corresponding to 50 into 60 liters, and that water will be available if collected today for tomorrow, right from the whatever is the time that you need. So, the effectiveness of the same system is enormously increased if you had no storage tank compared to providing storage. So, this is an extreme example I gave to drive home the point. The system performance can critically depend upon the component performance, though collector is an essential and most important component in the system. So, which we had already mentioned. The other thing is, we talk about long term performance. For example, your equation Q u equal to A C F r times I t tau alpha minus U L T f I minus T a is a short term. So, you repeatedly apply this equation for different solar radiation, different hours, different days, and sum up over the year, and you will find out what is the useful energy delivered by the collector, which we call the long term performance, which really means it is a laborious calculation, that is one part of it, but we will base our assessment of the system adequacy based upon long term performance rather than the short term. The time period we choose is 1 year. There are two good reasons for it, and one is economics is usually assessed annually. Then second thing is meteorological cycle. Repeats itself every year. I really do not mean to say that January 1 of 2012 will be identical to January 1 of 2013 or anything of that type of exact equivalence, but January average will be the same. If you look at it yearly average, it will be within plus minus 5% of any previous 10 years or coming 10 years. So, this is because of evaluating economic figures of merit, what we call is based upon annual performance, and also, and if we find out the performance of the system over a period of 1 year, it will be typical for that particular year, and consequently you can expect that this is the saving or this is the performance of the energy system that you have put, solar energy system that you have put over the year, because the season changes, the solar radiation changes, ambient temperature changes, consequently the performance of the collector and including even the losses from the tanks, heat exchanger, etc., could be time dependent. Consequently, you will expect the typical output per year so much. Now, how do we classify these solar energy systems? So, earlier I did not want to classify first and then go for it. We have a lot of radiation and optical properties processing, long term, short term. Practically, we are in a position to calculate the solar radiation on any tilted surface or tracking surface, and then solar collectors, flat plate or concentrating, we have collected enough detail, so that we can have a performance equation from which you can calculate the performance or the output from a solar collector for given input conditions like solar radiation, flow rate, etc., etc. However, we have two major things which we call the active systems and then passive systems. It is not exactly like you can classify a blood group 1 or blood group 2, there could be overlap, and it is a general understanding that there is no hard and fast demarcation between these two types. Generally, in active systems, you have a pump or blower circulating the fluid, and there may be heat exchangers. But this is not to say one can have a counterpart passive system like a greenhouse, which we will deal little later, which may have a small fan to exhaust the hot humid air. So, that is not a active system. Similarly, if there is no pump and if it is being circulated by thermosiphon action, still it may be considered a flat plate collector system, an active system. Then another way people try to clarify, saying that passive system is a part of the architecture. It may or may not be a part of the architecture, in the sense that in the building, if you house flat plate collectors along with the roof or along with the tilted roof and then circulate the water, still it will be considered as an active system compared to whatever it is independently installed over a rooftop or even on the ground floor. And you can give also a counter example for a passive system, which is a passive system, though it could be external to the body. For example, a solar cooker. Okay. So, you have a passive solar cooker, although it is an external device and it is kept externally, except it does not have a pump or a fan to circulate the fluid inside the device. We will deal with some of these things little later, but I think a popular concept of a solar cooker, greenhouse, you must have heard. So, which I have already written, that a solar greenhouse will be considered as a passive system even when it is separately constructed. For example, in cold climates, to preserve the plants or to keep them alive, to make the seeds, solar greenhouses are constructed, and as it is a very commercial proposition. In addition to this broad classification as active and passive systems, solar energy systems are classified based on type of collector, working fluid or application. So, you may have and even the control strategies. So, these classifications are not that rigid, there can be overlaps, and one should not be upset whether it is a passive system or an active system, but it should be understood in the spirit in which it is spoken. So, a domestic water heating system generally uses a liquid based flat plate collector and can be run on thermosiphon or with or a pump or without a pump separately installed, and it is an active system. Now, you may have, based on the collector system, flat plate collector, or concentrating. So, any system that uses the flat plate collectors, whatever may be the application, I may call it a system of flat plate collectors and a system of concentrating collectors if concentrating collectors are used. Then it could be based upon the working fluid, usually water or air. Instead of a water, it can be a liquid for certain advantages like antifreeze or even high thermal capacity fluids, and generally gases are not heated, most of the time it is only the air, and you may call it based on application. Third, so another way is functionality. Irrespective of what type of collector you used, whether you used a liquid or whether you used air and flat plate or concentrating collector, it can be a space heating system to provide comfort inside if the temperature is below the comfort condition of about approximately 20 degrees C, you try to heat it up with a space heating system, and it may be domestic water heating. I shall make a comment about the terminology a bit later after I finish these names. Industrial process heat, and then you may call it a solar drying system, entirely different from the above. And depending upon your application, it may be a low pressure steam system. So, what we are trying to do from a industrial process heating is distinguish it if it is steam or only hot water or something else. Then it could be a power generating system, if you restrict yourselves to only thermal systems, solar energy thermal systems, a power generation will be through a basically high pressure steam against the low pressure steam. And G, it may be a solar furnace, and H could be cooling systems, including absorption type or compression type refrigerators and cooling of the room or cold storages. And then you may have based upon control and operation. This is an important aspect. From the efficiency point of view or the effectiveness point of view, though not necessarily from the classification point of view only, you can have an open loop, say for example, you have got a collector, there is a pump to load. Simply it goes through the collector once and the output water or air whatever is collected and it goes to meet the load, which is an open loop system. The influence of this output has nothing to do with this input. Then naturally, you have a closed loop, something like this. So, you keep on recirculating the fluid through the collector, and though it is not part of the definition, I may have an exchange here with a heat exchanger like this. In other words, the energy collected by the collector after heating the fluid dumps the energy in a storage tank. From that storage tank you pick up to meet the different loads. The load loop does not interact with the collector loop except through the storage or the heat exchanger. And then you may have a on off system. Once again, this also requires a little bit of clarification. So, one can say that if this is the collector, the output and entering cold fluid through a pump, and you are having the directions like this. Now, if T F O is greater than T F I, then the pump is on, or it is off. This is typical on off system as practiced in the US, and of course, you may have it alternately. Pump on if somewhere at the T is higher or equal set temperature. So, this difference, this is also on and off of the pump, but the difference is the collector is in stagnant mode most of the time. This is also on off as far as the pump is concerned, but the operation is completely different between pump running as long as the outlet temperature is higher than the inlet temperature, compared to the pump circulating the fluid only if the fluid reaches the desired temperature. Then you have got a, of course, a better one, a proportionally controlled system. Basically, m dot is proportional to I t. So, you have a motorized valve which will sense if the solar radiation is higher, it will send a higher flow rate to the collector, and if the solar radiation is lower, a lower flow rate is sent to the collector. This ensures more or less a uniform temperature output, and the throughput, or the rather the water or the air being circulated through the collector being higher if the solar radiation is higher, and it is lower if the solar radiation is lower. Of course, the designated energy, temperature, the whatever you desire is set depending upon, as we discussed some time back, the critical level. If it is lower than the critical level, no matter how small the flow rate is, your temperature cannot be whatever the T minimum that you have set. So, you can see this picture, which I will try to redraw, which consists of a typical components in a solar energy system, which I also tell you that some of them can be absent or present, and you can equivalently model depending upon your need and depending upon the actual components that are present. Then from here, I may have an auxiliary over here, T load return with a m dot return, and this is auxiliary. This is sort of you can call it a delivery device. This is your storage. This is a heat exchanger which separates the collector loop from the load loop, and you have got here is a heat exchanger HX, collector and a pump. You may or may not have this heat exchanger. It may directly be dumping the energy into the storage, and there may or may not be a heat exchanger in between the delivery device and the storage, and another sort of heat exchanger before it meets the load, and before it meets the load there will be an auxiliary. Auxiliary, it could be an electrical heating or a boiler, which will make up either for the quantity that is desired if my solar energy system is unable to supply, or make up for the quality. Suppose you want T minimum at 60, but my T out is 52. So, what I can do is take this 52 heat to 60 in the auxiliary, or you need m dot flow rate meeting the energy temperature delivery, or the solar energy system is able to cater to m dot multiplied by some fraction. Okay. So, you can make up to match m dot with the auxiliary. So, I have shown here this so called auxiliary in series can be in series or parallel. Okay. So, if it is parallel, generally it is more convenient to do this makeup business, and if it is in series, it is more easy to match the quality. Now, we have got our challenge in the sense that compared to most of the other conventional systems, when you come to a solar energy system in general, in particular, or a environmentally driven system in general, what is the performance index? Is it the efficiency? If it is the efficiency, and we need say 1 year performance. So, useful energy gain for the year, is it eta times H T y? Obviously, this does not work, and even if it does, then this should be eta y should be a weighted average. Because we know that the efficiency depends upon the input solar radiation, ambient temperature, wind velocity, so on and so forth. So, if I want to have a typical yearly efficiency average, I should really sum up all my inputs multiplied by the efficiency and then divide it, which essentially means your calculations for the entire year. Then how do I account for that? Your energy delivery is more than the demand. You are not hungry, you are given the food, so will you pay for it? So, if the solar energy system delivers more energy than what is needed, of course, it goes to the storage tank, and over and above that it will go to the dump. Rather, it has to be not accounted for in terms of economic analysis. So, we have for a small period of time we have the efficiency, but if you consider a long period of time, we have to consider the performance over short periods of time continuously for the period of 1 year or 1 month or whatever we want. And the other thing which I was mentioning, if you plot even an ideal day, a solar radiation profile on the collector surface from the sunrise to the sunset, and this is my so called critical radiation level. This is critical level, which is obtained as I c equal to F r u l into T I minus T a by F r tau alpha, which is nothing but the radiation should be above this critical level in order that there is a heating up to T I. So, if you set the useful energy gain equal to 0, the minimum radiation required for the water to be heated or the fluid to be heated to T I is met. Okay. So, now this is my time period of operation. This changes because your T A may be changing, if your loss coefficients may be changing, solar radiation may be changing, and consequently, the operational period will be different. When I say that solar radiation changes, though this equation does not contain that, if this curve is like this and my critical level is here, okay, it is a lower radiation, then my operational period is much smaller. Sometimes there may be none. So, we need a long term output from the economic point of view, and also the repetitive nature of the metallurgical cycle being 1 year, you need a long term system performance. So, it has to be sort of weighted averages. The net useful energy in meeting the load will be less than that delivered by the collector on account of thermal losses taking place from the storage, pipes, ducts and further penalties due to the presence of heat exchangers either in the collector, loop, storage or load loops. And what we are basically I was trying to say is my performance cannot be linearly proportional as delivered by the collector. So, if the energy delivered by the collector is Q u over a short period of time, if the solar radiation is doubled, my useful energy is not doubled. Similarly, if you have got a particular type of control and there will be certain losses or a heat exchanger, there will be certain losses, but again those losses are not proportional to the useful energy gain as delivered by the collector. So, collector is important in the sense that it does give the useful energy gain, but what we are interested is Q u system. We would like to find out what is that part of the solar energy as delivered by the collector is going to meet the load. So, instead of a commonly thought of sort of efficiency, we will go for something else here. We have already said that excess storage will be dumped and consequently, it cannot be taken into account your economic calculation or in your efficiency so called calculation. So, this Q u system is not necessarily equal to QU collector. So, to drive home the point or to emphasize this aspect, if you say for example, have a ceiling fan and you give the voltage of 220 volts 50 cycles Indian supply, and wherever you keep it, it performs exactly the same way. Whereas, a solar energy collector, solar thermal collector, same design, you keep it in Chennai, you will get one output, and you will keep it in New Delhi, you will get another output. So, consequently, you cannot base that efficiency of the system or the device multiplied by some input is equal to the output. So, this is what makes the solar technology now a little bit challenging and interesting, and it is not like a conventional device where you take the overall input and multiply by efficiency to get the output. So, these things have to be done from location to location. So, now we will call it long term performance prediction. It is not a horoscopic prediction, it is you may call it estimation if you like it, because some people get allergic about predictions. So, it is a long term performance estimation for the solar energy system. That period we choose a year normally. The reason, as I explained, because of the meteorological cycle as well as the economic analysis. So, when we try to do this, we will not, I will write mathematically what I had explained earlier. So, let us say L is the load and Q call is the energy as delivered by the collector, and Q system as served to the system or load. In other words, you have got 500 liters of requirement, you got 498 liters, then the Q system is 498, and whatever is the Q collected should be equal to Q system. Now, this is written only for mathematical convenience. What all we are trying to say is L minus Q call superscript plus, which means if L minus Q call is positive, okay, you take that. So, L minus Q call equal to L minus Q call. So, that Q system is equal to Q call. So, whatever is, I am not talking about the losses, the principle is only that the system will not accept excess energy in the system, in the sense that you would not like to pay for what you do not want. If the collector supplies more energy, right, after going to the storage, still if there is an excess, for that the economic benefit cannot be assigned. So, we will write this in terms of this mathematical symbol, and if L minus Q call is less than 0, we treat, that means L is more and you have got Q system, if it is positive L minus L, that is okay, and Q system equal to Q col, right? Right. So, this should be L. In other words, the system cannot have more than the load. In the case of when the supply is less than the load, then equal to the supply. Okay. So, this has been put, I think, more clearly, and you can see this. This mainly arises due to non-uniformity in the energy delivered and load mismatch. So, efficiency, if you want to decide for a year, it involves a calculation of weighted averages. Then also it is only that of the collector. Then I am not able to combine it with the utility of the solar energy system in so far as meeting the load is concerned. So, we will define a F, the so called solar load fraction. This we will define Q system upon L, say for a month, right. So, this is the Q system is the energy that goes meet the load. Okay. I can even put a condition. Of course, earlier if you write Q system is equal to L minus Q col superscript plus, it takes care of, or else if f is greater than or equal to 1, set f is equal to 1, right. That means, the solar load fraction cannot be more than 1, even if the collector is capable of supplying higher than the load required. So, if that is for a month, I can define the annual solar load fraction So, it is a weighted average of the load fraction F I for a month I and the corresponding load L I upon L I summed up over all the months. Please recollect, remember that L I does change from month to month, at least. If it is day to day, it will be even more difficult. I have to define for each day, but what we can say that month to month is my for example, if it is a simple water heating system, T I changes. So, consequently, if you want water at 60, my energy M C P delta T differs, because my T A is changing, because I am assuming for the time being that I am drawing the water from the atmosphere, open atmosphere, which is effectively at a temperature T A. So, L I changes considerably. For example, even in India, where the weather variation is not that extreme. Say for example, typical December maybe T A is 15 degrees and maybe June T A is 38 degrees and I want at 60. degrees. So, delta T for December will be 45 and for this it will be only 22, right. So, it is almost half of this. In addition, you combine the fact December radiation may be 2/3 of the June radiation. But do not think of only for bathing, any other application. If my desired temperature is 60, the load on the system in the winter is almost 4 times that is the load in June, right. So, if you design for December, it will be a over design for June. Consequently, the effectiveness will be only the L, which may be so many megajoules if I express it in terms of energy units, and definitely the excess energy has to be put to some other use, but in evaluating this system viability it will not contribute. So, if I try to plot the solar load fraction F versus of course, the collector area, all other things will be parameters which I may have a curve 1, this will be of course 1 and this may be 2, this may be 3, I will give the numbers, this may be 4. So, 1, 2, 3, 4. So, this is deliberately not put monotonically. So, this is my solar load fraction. If the total load in the year is completely met by the solar energy system, it will be equal to unity, and it will approach to unity for pretty large areas, because at times it may be at least without an infinite storage, you may not be able to meet all the load throughout the year. So, it will reach 0.9995 and may not be 1 all the time. Okay. So, this is the nature of the curve. Now, first question is, why not linear? F versus AC, why it can't be? You double the collector area, it does give double the useful energy. So, why not the load fraction? The reason is similar to what I have explained in the context of month of December and the month of June. So, you have not been able to utilize the excess energy when it delivers, whereas when it does not deliver the excess energy, the penalty remains. So, initial very small area, there is no question of energy being excess of the load. So, it will increase as you double the area of the collector, it will double the utilization, consequently, it will initially linearize. Now, at a particular area something like this, it starts meeting the load fully, let us say in the month of October, right. Then subsequently November, subsequently December, if it is a winter application. So, my additional areas will be losing the extra energy delivered in the months of June, July, where the demand is less. So, the additional benefit of F will be decreasing with the increasing area. So, this is, let us say, in a mathematical sense, dF upon dAc no doubt is positive, otherwise you will not put any additional area, but second derivative is negative. In other words, solar load fraction increases with area at a decreasing rate. That is the mathematical, that is the physical meaning of first derivative being positive and second derivative being negative. So, first of all it is nonlinear. The reason for nonlinearity is expressed. So, we have marked the curves as 1, 2, 3, 4 like that. So, curve 1 can be for a particular location. Let us say Kharagpur. Okay. And 2 is at a, these features I have already commented on, this one also. Now, this curve 2 is lower than the curve 1. Let us just check it. Right. So, the solar load fraction at the same area is lower for curve 2. This may be a colder place, maybe Shimla. So, the same system if you put in the US, sorry, if you put it in the Shimla or a cold place, it will deliver energy may be the same or less, because my solar radiation is less, but solar load fraction will be less on two counts. Useful energy delivered by the collector is lower and the load also is higher if it is a space heating system, or even if it is a water heating system, simple, your T ambient or T minimum inlet temperature to the collector will be much lower than what it could be in Kharagpur or Chennai. So, curve 3 above 1, even at the same place like say KGP Kharagpur, may be due to higher storage. Okay, which means that dumping does not occur or dumping will be lesser. So, you will have in a month like June, if there is extra energy delivered, there is a large enough storage for that energy to be stored and which can be utilized in a lean day when it rains or a subsequent month like October, November, December. In principle, if you have a seasonal storage, the effectiveness will be very much improved, though one has to account for whether that large seasonal storage is cost effective or not. So, we shall in the next class try to find out how we can find out this solar load fraction. One way is to make a hour by hour calculation, or are there any simpler methods? Thank you.